Okay, so let's go ahead and do some hypothesis testing using linear regression. So, just as we identified standard errors for point estimates previously, we can discuss standard errors for the estimates for slope and y-intercept as well. The difference is that we're not going to be calculating them. The formulas for the standard error for these things are fairly painful. We'll just let the statistical software do it for us. Now, like everything else we've been doing this quarter, there are conditions. In order to deal with the conditions, in order to deal with the least squares line, and in order to do hypothesis testing using the least squares lines, we need to at least check these four conditions. Now, first off, the data should show a linear trend. And the main thing we want to avoid is we want to avoid any kind of bends in the data. That would be bad. So, something like this. That would be bad. Nearly normal residuals. The main thing for this one is that watch out for influential points. So outliers that are far enough away that they're influencing the results. Constant variability would be the next thing. And basically that means what we really want is something like this, where we have our line and we want the data points to be kind of within a band around that line. Doesn't have to be perfect, but that would be good. Something like this is where, there's sort of a band. What we don't want to see is sort of a cone shape. So this thing is good. Something that wouldn't be good would be something like sort of like that would be kind of bad. There it is. We don't like that kind of shape. And then independent observations. Essentially for us, that means watch out for time series. But if you randomly select from less than 10% of the population, you'll be fine. Otherwise, we need to make sure that data is not collected sequentially, or we need to be cautious if it is collected sequentially, such as like a time series. And so here is an example that these are four graphs that each of these fails one of the conditions. This first one here fails the linearity condition. You can see both with the graph and the regression line that there's a bend in the data. So really, our linear regression is not the best choice. The next graph, it could be a little bit better example, but this is sort of one that kind of fails the nearly normal residuals condition. And that we have sort of an outlier here. I don't know if it's extremely influential. I'm not sure that one would really matter. I think something that was something farther away, like about here, would be much more of an issue. But anyway, this is sort of what you want to look out for in terms of the nearly normal condition. The next graph fails the constant variability condition. Now, if you look at it, you have this cone shape. You can see it both with the graph and the residual plot. So we don't like that. That fails the constant variability condition. And the final one, little tricky, without context, but this is something you kind of see with a time series. It's like if you're plotting stocks from the stock market, or gas prices, or inflation, or things like that. Something like this, where a line is maybe not the best fit. That kind of shows up in a time series. All right. So for my example today, I'm going to go ahead and talk about midterm elections and employment. Elections for members of the U.S. House of Representatives occurs every 2 years, coinciding every 4 years with the U.S. presidential election. The set of House elections occurring during the middle of a presidential term are called the midterm elections. In America's two-party system, One political theory suggests that the higher the unemployment rate, the worse the president's party will do in the midterm elections. So here's the graph of basically every election from 1898 to 2010. Every midterm election, I should say, from 1898 to 2010, with the exception of those elections during the Great Depression. And I'll show you why a little bit later. But to assess the validity of this claim, we compile all the historical data, look for connection. So again, the red triangles are the Republican, when it was a Republican president, midterm election. The blue dots are when Democrat was the president at the time. You can see here is where 0, this line right here represents 0. Everything below that would be based on midterm election where the president's party lost members. So you can see that almost every case the president's party did worse. There's 2 exceptions where Clinton in 1998 and Bush in 2002 both did a little bit better. Not by a lot, but both actually saw increases. And those are the only 2 times. Everyone else seems to have done worse. So again, the figure below shows data, and here's the least squares line. That basically the percent change, this is basically predicted, so it's sample. Percent change in House seats for President's Party is negative 6.71 minus 1.00 times the unemployment rate. So the negative 6.71 means that when the unemployment rate was 0, the President's Party would still be expected to lose 6.71% on average. Well, anyway, it doesn't matter. This is an extrapolation, so don't put a whole lot of faith in that number. The other one, the -1, basically is saying that for every percent increase in unemployment, the President's Party loses an average of 1% in the House. Maybe sometimes more, sometimes less, but on average, every 1% increase in employment is associated with a 1% decrease in the President's Party for the House of Representatives. All right, so interpret the slope and the intercept in context. Well, I think I just did. Okay. Well, one more time anyway. The negative 6.71, this number occurs when the x value is equal to 0. So when the unemployment rate is 0, the President's Party is expected to lose 6.71% of their members in House. Again, don't put a whole lot of faith in that number. It's an extrapolation since the unemployment rate's never been 0. But anyway, that's what the number means. The other number, the -1, that basically means that every time the unemployment rate increases by 1, the percent change decreases by 1%. So for every 1% increase in the unemployment rate, the percent change in the House is -1% for the President's Party. So examining the data, there's no clear deviations from linearity. I mean, it's not really great data, but there's no real clear bends. The constant variability, I mean, really, again, not really great data, but everything is kind of within a band, so you don't really have that cone shape. No real outlier. Well, for this, there were outliers. I'll get to those a little bit later with the Great Depression. But not including the Great Depression, there's no obvious outliers. While the data are collected sequentially, I mean, we're doing every 4 years, there was a separate analysis done to check for any apparent correlation between successive observations, and there was no such correlation was found. So that means a linear regression, the conditions for linear regression seem to have been met.